Hi guys, we're going to be going over higher alkane halogenation today. If there's some background noise, I apologize for that. I don't know what's going on outside, but it's kind of funny. So anyway, we have our final exam tomorrow. It's kind of late, but I thought I'd make a video anyway. But yeah, it's kind of fun. So on the board, what I have is, I have two problems. So this one is a normal alkane plus a halogen yields an alkyl halide plus an acid. So basically what we did was we took off a hydrogen from the CH3, we took a chlorine, merged them together, and then merged this little section together too. Now I really want to make it clear that what sets us apart from normal alkane halogenation is that we have this guy here. It's either going to be energy, heat, or light. It's very important that if you were maybe drawing a synthesis or writing out a synthesis, that you include this little symbol. All right, so what's the difference between that one and this one? This one is a little bit more complicated. So in this one, it was symmetrical. We could pull off the hydrogen from this CH3. Oh gosh, I wrote this incorrectly. My bad, guys, my bad. Maybe I should, I don't think I'm going to restart, but I really apologize for that. But basically, this is symmetrical. This is asymmetrical, so we can have multiple points, different points of attachment for this chlorine. We could have one here at this CH3. We could have one at this CH. We could have one at this CH2, and then at this CH3. But what about this guy over here? So the way you have to look at it is first you have to look at the carbon-hydrogen compound itself. This CH3, I mean, we have 3 CH3 little guys in our compound, right? Then we need to look at the connectivity. So this CH3 is connected to a CH. Okay, this CH3 is connected to a CH. So they're basically the same, and they will serve as one unit. Now let's go look at this CH3. This CH3 is connected to a CH2. Our other CH3s were not connected to a CH2, they were connected to a CH. So we're going to count that as its own little unit too. Basically when I mean units, it's areas where the chlorine can attach. And then CH doesn't show up anywhere else. So that's its own. And then CH2 also does not show up anywhere else. That's also its own little unit. And again, these 1, 2, 3, and 4 different possible sites of attachment for chlorine. Now, when I talk about chlorine, we have to go into a little bit more depth because chlorine is not highly selective, or not as highly selective as bromine. So for this reason, when we're figuring out where the major product is, basically where the chlorine will fit and make the best product, we need to look at 2 factors. We need to look at 1, stability. Okay, when I mean stability, is it a 3', tertiary, secondary, primary? Which one of these? And then we need to look at its rate. And the rates are, there's a parallel, or there's a connection between stability and rate. For chlorine specifically, it's always going to be, if you're tertiary, it's going to be 5, and then it's going to be for secondary 4, and then primary 1. So you guys need to remember this little guy. This is very, very important because we're going to be calculating some percentages in a little bit. All right? Hopefully this makes a little bit of sense. So now let's actually get started on the calculation itself. Am I running out of space? Maybe we'll go this way. All right, let's start with the first carbon. If I were to attach Cl to this first carbon, this is what my molecule would look like. I also want to stress that everything makes Lewis structure sense. Make sure everything fills up the 4 carbon bond rule. Remember, carbon likes to make 4 bonds to fill out the valence electron, or to have like a complete shell. So this is our first possibility. If I were to draw number 2, CH3, C, the chlorine would be attached to my second point, CH2, CH3, and then I think it's CH3 here. Then we have our third possible structure, which is going to be here. So CH3, CH. On this next one, I'm going to have my chlorine attached, and then I have my CH3. My CH3. And lastly, I think y'all can see it. When I do my fourth one up here, guys, I'm so sorry, it's so messy. Which will be here. So keeping everything else the same, but that fourth one, where I'm gonna add my chlorine and then my methyl group. So these are the four possible structures that we could possibly, or four possible compounds that we could have with this alkane halogenation. And it's considered higher alkane halogenation because we have multiple sites of possible attachment. It's not just this nice little symmetrical guy, or even if I had a methane, you could easily just say it's going to be, we only have to pull off one hydrogen, only one place to pull it off from. Easily say this. Sorry, Cl. That's not the case. So anyway, so what do we do from now? Let's look at whether they're primary, secondary, or tertiary. And when we do this, we need to look at where the halogen is attached to. So this halogen is attached to this carbon. We're looking at where the carbon that the halogen is attached to, what it's attached to itself. This is a 1', or a primary, my bad, I keep saying that. And then if we go to number 2, this carbon is connected to 1, 2, 3, making this a tertiary carbon. And then if we go to this one, this is connected to 1, 2, making this a secondary carbon. And then up to number 4, our Cl guy, its carbon is just connected to 1, so this is going to be a primary. So next what we're going to do is we're going to use our rates, because we said these are the two factors that we need to take into account when we're making our alkyl halide, or alkyl halide. So we need to look at rates. So primary, that's got a rate of 1. 3 tertiary has a rate of 5. And then my secondary has a rate of 4. And going back to my primary, it has a rate of, 1. So now we need to do our calculations. And the formula for our calculation is rate times the number of hydrogens is going to give us part of a fraction. So let's do this. So for 1, we have to look at the original compound. We have 2 ones here. That's 6 hydrogens being affected total. 6 times 1 equals 6. So let's do this one. Okay, what do y'all think? So we're going back to this original compound, number 2. We have 1 hydrogen attached to this carbon. We have no other CH compounds with the same connectivity. So we're going to do my rate, which is 5 times 1 hydrogen. 5. Yes, these numbers should be switched. Oh gosh, sorry guys, this takes a little bit longer than I thought. And then if we go here, this is our number 3. We only have 2 hydrogens connected to it, and our rate is 4, so 4 times 2 is equal to 8. We go up to this bad boy. Going back to number 4, it's connected to 3 hydrogens. It's a primary, so the rate is 1. 1 times 3 equals 3. So now what we do is we add all of these up. So we're going to add 6, 5, 8, and 3, which should give us 22, I believe. And we're going to divide it by 22. So what I did to get this 22, again, I did 6 plus 5 plus 8 plus 3. Okay? And then we're going to multiply it by 100 to get our percentages. Okay? And let me look at my notes because I don't have a calculator. We end up getting 27%, 23%, 36%, and then 14%. So which one has the higher percentage? It would be number 3 because we had 36%. So that means that number 3 is our major product. And that would be contrary to what we think because, well, hey, this is a 3', or this is a tertiary carbon connected to my halogen. So why isn't it that one? Well, it's because we have to look at these two factors. We have not only stability, but rate too. And this is all in the presence of heat, light, and energy. Because if we didn't have this, we could just say, okay, well, we can just look at the stability, but because again, we have heat, light, energy, we must look at the rate. So this number 3 is going to end up being our major product. All right, thanks for watching, guys. I had a lot of fun doing that. I don't know if it was at all understandable, but good luck with everything. I'll see you later.